Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 5, Limiting Distributions, and we're in the fourth video on this little mini-series. So let's jump into today's topic where we left off, and it was this example. Now, this example illustrates why we use CDFs when we're looking at convergence and distributions instead of PDFs, because PDFs don't often behave nicely, so we can't use them. So we have to use CDFs. And this is an example to show that even though the CDFs converge to a nice CDF, the PDFs don't converge to a nice PDF. So let's let n go from 1 to infinity and define this PDF, f of n, which has 2 points, and one point is 1 minus 1 over n, and the other point, is 1 plus 1 over n, and each have a probability of a half. So this is a proper PDF, and the CDF of this would be this. So it is 0 when we're below this point, and when we're between them, it's 1/2, and when we reach that point, it's 1. And if we note that if n goes to infinity, f of n converges in distribution to f of x, which does not depend upon n, which is this. And I'll show this graphically and it'll make more sense if that seems confusing. That f of x is 0 if we're less than 1 and 1 if we're greater than or equal to 1. However, this PDF does not converge. However, the PDF f of n does not converge to a valid PDF. F of n converges to f of x, which is 0, and this is at all x. Okay, to illustrate that, let's look at the PDF. And so this is the density. So we have 2 points at 1 minus 1 over n and 1 plus 1 over n, and they're each a half. So you add them, it is 0. Now as n increases, these lines, both of them start merging towards 1, and at any given n, it's still a valid PDF. But as n goes to infinity, this converges to 0. And here's the illustration. Let's pick a point, say right here. And I don't know that exact number, but as n goes to infinity, these lines converge, and it may end up being on that point. So we get 1/2 at maybe at some n, but then afterwards, these lines keep going towards 1, and the value of x that we picked will remain 0 forever. So that value of x has a limiting value, of 0. Well, it turns out any x that we pick, when n gets large enough, these lines will bypass it, and the limiting, it limits to 0. So that means the limiting PDF is 0, which is not a valid PDF, right? It doesn't add to 1. Now the cumulative distribution function is this. So for any, I think this is for n equal 5. I'm not for sure about that, but at this point it's 0, and then it jumps up to 1/2, between them, and then after you get past it, it goes to 1. But as n increases, this gets shorter, this moves towards 1, and this moves towards 1. So any value that we pick, it's either going to, if we're below 1, the limiting value is 0, and if we're above 1, the limiting value is 1. So that 1 is not a continuity point, so we can do whatever we want with it. So we just say, when you're at 1, make it 1, and then that's a valid CDF. So approximations for the binomial distribution. First a note that a binomial random variable as a sum of Bernoulli random variables. Now in a previous example, we took a random sample from a Bernoulli distribution with parameter p, and we showed that if we add them up and then call that new random variable yn, that's a binomial distribution with parameters n and p. So this is the key point. Every binomial random variable is equivalent to a sum of Bernoulli random variables, which means the central limit theorem can be applied to approximate a binomial random variable with a normal random variable. So let xn be binomial NP, and I should say an N large, then the approximate distribution of xn, and that's this, there's a dot there, which means approximately distributed normally with mean NP and variance NPQ. Okay, so that, and then one other point is what's called a continuity correction. I'll illustrate this in the graph below. It's adding or subtracting 1/2 into, when we're approximating the binomial with the normal, we add what's called a continuity correction. And let me illustrate that with a picture. Okay, so this plot here is a binomial with n equal 10 and p equal 0.22, and then the normal densities overlaid. This one here, n is 10 and p is 0.5 with the normal density overlaid. If we just look at this one here, the probability that x is 4, remember x is a binomial random variable, is actually this height. So it's 0.2. That's it. That's the probability. But notice that if we add 1/2 and subtract 1/2, the area of this rectangle is actually equal to the probability that x equals 4. But when we use a normal distribution to approximate a binomial, we can't say the probability that x equals 4 when we're using the normal, because the probability at any point is 0. But if we add 1/2 and subtract 1/2, and then we look at the area under this normal distribution, that is approximately the area of this rectangle. Because notice that this little piece can fit into there, and it's really a close approximation. Anyway, but that's what's called a continuity correction. It's used in lots and lots of different cases where the normal distribution approximates a discrete distribution. These approximations, so using the normal to approximate the binomial, the accuracy increases as n increases. So here's n equal 200, p equal 0.2. And notice that all the little areas are much more close. In the same way with n 200 and p equal 0.5. So if we are using the normal distribution to approximate the binomial, it becomes really, really accurate. Okay, and so I think that's the end of page 12, and I was going to try to do 3 pages each video. So the next video we will start off with the example of a normal approximation to a binomial. Hopefully you enjoyed this. I sure did. Please like the video and subscribe to the next one. Thanks. Bye.